So I'll be working on some concepts for the linear algebra geometric approach from that textbook. I'll be going, I guess maybe I'll just scroll through some of the chapters and then uh, go over some of the concepts that was covered in sections 1 through 4. And so first I'll just look at an image, look at a little part of it, and then we covered that thing. I'll just talk about it a bit and see if I have about an hour before the exam. So I'll like spend an hour doing this, and then I'll take a break, and then I'll see how I do on the exam. All right, so let's go. So we'll start with vectors, and I'll show to make the book primary. I mean the screen. And we left off, by the way, proving that a line with a point that has the same vector as one of the vectors that make a plane, the point, the XO of that line is also in the plane. So now we'll say concepts 1.1 through 1.4, right? So vectors have length and direction, or magnitude and direction. Length is magnitude. So if you have a vector, let's say you have a vector equals x1, x2, which is the same thing as how we used to do xy. But it seems like in linear algebra, since we're going into different higher dimensions, so for instance, this would be R2, is how many terms are in that vector. But if you get into, let's say, R1005, you have to, do a whole lot of letters. So it's probably better to do X1 and then X1005. So that seems to be the reasoning behind using sort of a subscript on a letter when you get to linear algebra. So I wanted the length of this thing. That's the same thing as the magnitude. We use a double absolute value sign. And that's going to be the square root of the first term squared plus the second term squared. And that equals the length of the magnitude. Um, the direction, well, the direction is not, technically, I guess it is necessarily in the point. Because if we have this point here, this will be x1, and this will be x2. So we can say that this will be the vector that we're referring to. So I'll call it x. So that means that the direction, we can call this angle theta. So cosine of theta equals adjacent over hypotenuse, which equals x1 over, you could say, the magnitude of x. And be the magnitude of this as well. So you can say theta equals cosine inverse the magnitude of x1 over the magnitude of x. So let's test this. Now let's say that x1 equals, so we know a 3, 4, 5 triangle. So let's say x1 equals 3 and x2 equals 4. So we know that the magnitude of x is going to equal 5. And the magnitude of the adjacent is going to be the magnitude of uh, 3, 0, which is square root of 3 squared plus 0 squared, which is square root of 9, which is 3. And we know if the magnitude of x is 5, we need something that the square root of the two things sum to 25. So we could even say that we have 4 squared plus 3 squared from the fact of the 3, 4, 5 triangle, which makes sense because x is going to be x1, x2, which is 3, 4. So of course it is going to be the square root of 3 squared plus 4 squared. So that's working out. So the magnitude of that is 5. So we have theta equals cosine inverse of 3 over 5. And we know that that works out. So that makes sense. And theta happens to be 53 degrees, 53.13 degrees, or it says 0.92 radians. Zero 0.29 pi, or 0.3 pi, right? That's fair enough. Uh, so it says 2 points on the plane determined by a directed line segment, right? So a directed line segment. So what it's saying is that we have a plane and we have A and B. The directed line segment between these two, you can write as A, B with a line over the top. And actually is an arrow. I'm pretty sure I remember seeing a line, but so AB equals B minus A. And that's going to give you the length of that line segment. And therefore, some real number T, BA, B minus A, with T being real, will be a line that spans or that goes through these 2 points. So this would be T, B minus A. If you remember, we actually solved the problem using that uh, when we found, here it is here, the distance between L and W. We utilized the line segment thing right here. So that comes in handy if you're trying to find the length of distance between 2 points, getting that line segment, and then simply getting the magnitude of that line segment. and you get the length of that distance. In this case, it was the projection of P onto A, which is the distance from the point W to the plane. So it's very useful. So we basically just did this, except they're adding the additional detail that so in my problem, I made it pretty simple because it was based at the origin. So this is 0, 0, and this point was 3, 4. But still, the length of that line segment is going to be the magnitude. So if I call this B and I call this A, the magnitude of B, A, which is B minus A, which is, of course, 3, 4, since the origin is A. So we did that, but that's the more general form would be taking these points A and B, and recognizing that A is A1, A2, and B is B1, B2, and thus you could insert these there and find the line segment for any 2 points, no matter where they are on the plane. What does it have to be just at the origin? So scalar multiplication. You can scale a vector. So if x is a vector and alpha is a real number, then alpha times the magnitude of x is going to be alpha times the square root of x1 squared plus x2 squared. Now, I'm going to add a few steps here. This is like saying alpha, the magnitude of x1, x2, which equals, so apparently we can just distribute the scalar inside, which makes sense because if I have a point A equals A1, A2, if I were to double that, then it will simply double each of the components and make that line twice as long. Then you have 2A1 and 2A2. So you can do the same thing with the magnitude, which means that now we have the square root of alpha x1 squared plus alpha x2 squared. So that's going to be the square root of alpha squared x1 squared plus x2 squared. And now we can factor out the alpha squared, and then it becomes alpha x1 squared plus x2 squared. And we know that that is the magnitude of x. So that's going to be the same thing as the magnitude of x within the magnitude, both. So in a sense, since the scalar is just the magnitude, you can pull it out the magnitude because just like how we did up here, where x happened to be 3, 0. So this was A1 and A2. We know that works. So pretty much the same thing, an extension of that. So remember that the scalar inside the magnitude of a vector is the same whether it's inside or outside, right? We have a unit vector with the magnitude of x equals 1. That means this vector is somewhere, but the length is 1. So basically, you can see every vector is some scalar times a unit vector. Right? So to get the unit vector, all we have to do is take a vector and divide it by its magnitude, which I still think is odd. So the book has the example x equals 1, -2. So this vector is in a certain direction. It has a certain length, whatever it is in a direction with the length. So we divide that vector by its length, and all you're left with is a direction. So sort of like if you have uh, 5 times 4 divided by 5, you're just left with 4. So you can say 5 is like the magnitude, and 4 is like the direction. So by dividing by the magnitude, you're left with only the direction as a sort of analogy. So the magnitude of x equals square root of 1 squared plus -2 squared equals square root of 1 plus 4 equals square root of 5. So that means the unit vector equals 1 -2 over square root of 5. And if we were to test this and take the magnitude of that unit vector, it's going to be the square root of 1 squared plus -4 squared over square root of 5 squared and the square root of that. So that's going to be square root of 5 over square root of 5 equals 1. So definitely works. But I guess what seems odd to me is that you're dividing the magnitude by this vector could end up being a crazier number, but it just, since that vector has a magnitude, however ugly that vector looks, its magnitude is its magnitude. You divide by that, and that's what it is. So two non-zero vectors, x and y, are parallel if one vector is a scalar multiple of the other. And we did this problem earlier. When we did the proof, we found that u and v, they were parallel. Their span made a line because one was a scalar multiple of the other one. So we did that problem here. And if no scalar can make x equal y or y equal z, then that means that they're not parallel. Easy enough. Vector addition. I'll skip vector addition for now. Vector subtraction. Now, this is some very proofy stuff. The diagonals of a parallelogram bisect one another. So I did some of these earlier. Let's go to some more regular lines, regular concepts or lines. This is an important detail. A line is going to be basically some point whether it's the origin or any other point, plus some vector. And we did this one earlier when we drew it out here. So basically you have a point, and from that point, we'll be scaling some line in various directions. So this will be XO, this will be X, and essentially this distance here, this will be the XO plus alpha V. We'll just say C for whatever constant. And technically, I wrote that incorrectly. That'll be technically X equals XO plus C V. This would actually be X minus XO, or XO minus X, which I always think is odd, but to get the intuition about it, if you have two vectors and you add them, then the sum will be longer. But if you have two vectors and you subtract them, then it's going to be shorter. So these are the resultants from either adding or subtracting those two things. So we call this A and we call this B, and this would be A plus B, and this would be A minus B. So that's definitely important to keep in mind. Right? And this is called the parametric equation. So especially when we do Profi stuff and they want us to turn one into the other, this is the parametric equation of a line. And so let's write this again. Parametric and my writing program froze. Let me restart it. So to do this, parametric equals X equals XO plus TV. And if I was to make that into a Cartesian, I should be able to go X minus TV or X plus alpha V equals XO equals XO. Technically, this is the Cartesian. If I was to make this another vector, let's see if we can find that. Right. So it says consider this line. Yep. So this is the Cartesian. So if they have y on one side, It's like they're doing a bit more to make it Cartesian. So what we need to do is it's always easier to go from Cartesian to parametric than the other way around. But let's see if we can figure this out with this problem. So this t needs to be distributed. So we can actually call this the alpha and b would be vectors, and this would be a point. So excuse me, a variable. So you see how there's uh 0, 1 plus x1 and that, and then the x1 came from the t. So basically what happened is this will be x2 and, or I should say, right? Why don't we do this problem specifically, see if we could work it backwards. So we have the line x. Now what I'll do is start it in the other form, y equals 3x plus 1. So that's the sort of line that we're used to seeing. So I'll also make this y equals 3x plus 1. That's that. So now we're going to put it into the form x2 equals 3x1 plus 1. So now we have a value for x2. So we can say x as a vector equals x1, x1, x2 equals x1, 3x1 plus 1. And now we can factor out the numbers. So that's going to equal x1, x2. So that's going to equal x1, 3x1 plus 1. So that's going to equal 0, 1 plus 1, 3x1. So that equals 0, 1 plus 1, 3x1. And that's still equal to the vector. And now x1 is just a variable. So we have 0, 1 plus 1, 3, t. So this line is going to go in this direction, and this is going to be the starting point of the line at xo. And it's going to be scaled by t. So let's take this in reverse. And we can say x equals 0, 1. And this is the parametric, by the way. So now we're starting with a parametric of a line. And I'm going to call randomly that x2. Because I see that it's an R2, because I only have two components here. So now I can say this equals 0, 1 plus x2, 2x2. So this equals x2, 1 plus 2x2. And so now we have it. x1 equals x2 equals 1 plus 2x2. So if x equals y, if x1 equals y and x2 equals x, we have y equals 1 plus 2x, or equals 2x plus 1. And this is the Cartesian. So it still seems odd going the other way, but all we have to do is just get one term completely in terms of the other one, and then just call it that. So x1 is totally in terms of x2, and now we can put x2 equals, or x1 equals 1 plus 2x2, and now this is a Cartesian. All we have to do is put it in familiar form. So the parametric is always going to have a vector times a scalar plus a point, whereas the Cartesian will have one thing in terms of another. So that's the best way I can describe the two. Right? Now, one detail I forgot about, the book is pointing out how to find the Cartesian a different way, even though I like this way, it's good. So we know that we have a point with a direction. The direction vector determines the slope. So the direction vector is the slope, not the normal. So basically, the direction vector v, oh, I made a mistake and rewrote my 3 as a 2, but I'll just put that 3 instead be 2. Doesn't matter what the number is. But so when you're dealing with the vector itself, m equals 3 over 1 equals 3, or m equals 2 over 1 equals 2. But if you're dealing with the normal to that vector, equals the reverse, it's going to be negative 1 over 2. So when you have a normal and you put negative x over y, that's going to be the slope. But if you have the vector, then it's going to be directly y over x, rise over run. That's directly the direction the vector is going in. right? Length, scalar multiplication sum, got that. It is doing it in greater dimensions. We covered how a plane is two vectors. Sometimes at a point, if it starts at a point, then we know it's shifted from the origin. It's non-homogeneous or heterogeneous. We'll like to look at one more time at that example, other way of getting a Cartesian. Always seems strange to me. Maybe I should stick with this way. That makes sense to me. I shall do that. And we do see that the slope is 2, just like that method gives. So I'll stick with this method for now. It should work regardless. Just going the reverse way. Dot product, very important. So the dot product of two vectors has these properties. X dot y equals x1, y, x1, x2 dot y1, y2 equals x1, y1 plus x2, y2. Now, some inherent properties would be x dot y equals y dot x. So I believe this is a commutative property. You can do it either way, either direction, just like adding math, regular numbers. So x dot x equals x1, x2 dot x1, x2. So that's x1 squared plus x2 squared. So this is the same thing as the magnitude of x with the square root taken off. So it's like the magnitude of x squared because that takes the square root off the magnitude. And length is always positive or equal to 0. So this is going to be greater than or equal to 0. And it's only 0 if x equals 0. If and only if. And it should go either way. Magnitude of x equals 0. Right? So we sort of looked at the scalar before in another context. So the scalar of x dot y equals the scalar of x dot y equals the scalar times the whole thing dot y. And now we find it should also equal, even though it's not listed there clearly, it should equal the scalar of y. Because no matter how you look at it, it'll end up being c x1 y1 plus c x2 y2. Which means you can factor out however you want. You can say either C x1, C x2 dot y1, y2, or you can say x1, x2 dot cy1, cy2. By the way, and this is actually my favorite. This one here, which is if you dot product to a sum, you can distribute the dot product, and it's x dot x plus x dot y. So notice that the sum is being dotted. This is not, so in other words, this won't work. If you have x dot y plus x dot z, you cannot distribute these or extract these in the same way. So did I write that wrong? But I meant to say, I wrote the same thing. What I meant to say is if you have x plus y dot product x plus z, you can't factor these in the same way. So it's only if the dot product, if the hold up, that's still not what I meant. That's because it's wrong. It's hard for me to remember it. Yeah, this is what I meant. So if you have x dot y and x dot z, that's not how you would factor it. No, it is. I can't write it the wrong way. I did it wrong one time, but I don't remember how to write it the wrong way exactly. So maybe that's a good thing. I won't forget it in the exam. So we already showed how you can factor this either way with the scalar. We already talked about how you could sum the vectors in that way. So another detail is if two vectors are orthogonal, their dot product is 0. So if this is x and this is y, it doesn't matter how long they are, the dot product equals 0. Similar to how we learned earlier that the normal to a line, the slope is reversed. If you have the normal vector, the slope is negative x over y. And if you have the actual vector, then it's just y over x. So dot producting those inverses will give you 0. So it's kind of like 1, 2 dot product 2, negative 1. So now you're going to have 2 minus 2, so it's going to be 0. So that seems to be where that comes from, because the normal is the absolute flop. And it's also the other line, and that you're dot producting those two things. That's the numbers are swapped and one sign is swapped, so it's going to cancel each other out, which is easy enough. And we talked earlier about how the sum is longer, the minus is across. We looked at a problem with the projection and what C stands for. Let's look at these. So we'll draw this out. I'm looking at this right here. Maybe I should move this a bit in case I forget to maximize it again. Won't be as zoomed in, but it'll at least be visible. Right? So we're looking at the fact that so we'll take x dot y. So we have x and y. You can say that y, and they're splitting up x. So let me split up x. You can say x has a component that is parallel so that this line makes a right angle, and x also has a line that is perpendicular. So this is a right angle, and this is a right angle. And that's simply breaking up that x into its component vectors. So this is x perpendicular to y and x parallel to y. So in essence, when we take the dot product of x and y, we can also substitute in the sum of those two similar to the property earlier, which is probably why they introduced those properties, plus x parallel to y dot y. And as we saw earlier, when the sum is dotted to something, you could distribute the dot. So now we have x perpendicular to y dot y plus x parallel to y dot y. And as we went over earlier, the two vectors are perpendicular. The dot product is 0. So that means that the dot product really only looks at the parallel, the projection of one vector onto the other, and dot products those. So this is really just the parallel component of y, excuse me, the parallel component of x onto y, dot product y. And we know that the parallel component of x onto y is going to be some scalar of y, dot product y. And we can see this because y is out here, and this projection is shorter than y. So it's y scaled by some amount. And we know that y dot y is the magnitude squared, as we covered earlier with x dot x right here. So that means that this scalar is going to be the dot product of x and the dot product of y over the magnitude of y squared, which is what the book has right there. That's where that comes from. And then we can say, now interestingly, they also did this for the parallel. Let's see where they jumped in at. So it looks like they jumped in right here. and said, nope, didn't jump in there. Where did they jump in? So, not quite seeing how do you get the x parallel one. Oh, I see. They called it, I'm used to thinking about it as a projection. So the other side would be the projection of x onto y equals x parallel to y. That equals some scalar times y. So you can say that all the scalar equals the projection of y onto x divided by y, or the parallel, the parallel aspect of y divided by the vector y. So now I can make these two equal to each other, and I can say x dot y over the magnitude of y squared equals the projection parallel aspect over y. So that means the parallel aspect equals x dot y over the magnitude of y squared times the vector y. And it also equals the projection onto y of x equals that. All right. So I have to remember that this can be, that these are the same. I used to thinking about this only as the uh, projection, but these are all the same, right? So that came in handy with several of the problems of trying to find the distances to planes. So that is a very important relation. And the detail to remember is that there is a version where you have x dot y equals cosine theta times the magnitude of x and the magnitude of y. But that's not the one we need for this relation. We need the scalar, whatever the scalar is. Now, the fact is, we could also include that and say, I'll just use the projection. Well, we could use them both. We could say the projection onto y of x equals the parallel version of x. So that's going to equal magnitude of x times the magnitude of y cosine theta divided by the magnitude of y squared and y. So we can say that as well. So I don't think we really use that, but I suppose we can find some angle between x and y and make use of it if we needed to. And I do believe, well, if we was to take the magnitude of this whole thing, you could then, we could start canceling some stuff out, but I don't think we can cancel at this point. So we see that the dot product is really product being the parallel components as they have here in this image. So now they have the perpendicular. Oh, it's x minus x parallel. That's interesting. And that is true. X minus x parallel with x parallel going here will be the perpendicular. So that means that x perpendicular equals x minus x dot y over parallel y squared y. So that is interesting as well. I think I missed that one the first time around. So now we have an equation for parallel x and perpendicular x. Just by remembering the fact that the minus is the short version. So that is a very powerful uh, thing to remember, that if we have x and we have y, this is going to be x minus y, and this is going to be x plus y. All right, so I think this feels like a good place to stop. Have about 20 minutes before I start logging in for the exam. Wish me luck, and hopefully I do well. There's a little bit of leeway in that the fourth exam replaces the first one. So if I do bad on this one, I know I just need to improve my study processes and do well on the last three. Without I'm certainly not gonna make an A out of this class, whether I do well on this one or I have to make sure I compensate for the later ones. So wish me luck. And I think what I'll do next time, since I'll have this exam in linear algebra that I've been building to, perhaps I'll do a quantum physics reading next. So I've been feeling like I've been falling behind on my quantum physics reading. And maybe some astronomy reading as well. What I'll do is find my textbooks for the coming semester. Maybe I'll take a break during the break. I might look that up. And I'll start swapping some of those in more regularly. So be sure to like, subscribe if you haven't. Join my Discord. Sign up at my links. And I'll see you all soon.